Oh, okay. All right, so I asked everyone to watch the video on continuity, but I would never expect that you would have a perfect understanding of it. So I'm assuming there's questions, but let me first start by just taking a look at this graph and discussing a couple of things on it. First of all, we could talk about limits and not even deal with continuity at all. Right? We could come in here and we could say, let me see, this is 3, this is 2, 1, -1, -2, -3, -4. So remember, for a limit to exist, you have to check, what, both sides? Right? So like if I came in here, I said, you know, what's the limit as x approaches -3 of this function, with that little minus sign up here, which means you're going to approach from which side? Left side. What would that be? 2. So this is 1, this is 2, this is 3. So that just means that as we come in from here, approaching -3, the function's value from the left side is 2. Yes? But if I change that plus to a plus here instead, would that change the answer?
Yes.
Yes, that would be what? 1, right? Coming in from the right, it would be approaching a value. It looks like 1, maybe a little lower. Yeah? Okay. So what would the limit be if I don't put that at all? It wouldn't exist because it's not the same from both sides. All right, so what about this? Let me go to 0. Change it to 0 here. Would that limit exist? Yes? It would be what? 1. Because as you approach 0 on the function from both sides, it's approaching a value of 1. So the limit, remember, never dealt at all with actually what was happening at the value, right? But that's where continuity comes in. Continuity combines the limit and the function's value together at the same time. And so that to be continuous, you need to be able to satisfy an equation. And that's what, I'll put it up here, is the big continuity. Limit as x approaches a of f of x. So this just says, this is the definition of continuity at a point x equals a. So when we talk about continuity of a function at a single value, we need that the limit, first of all, exists. Right? This right here means from both sides, right? But not only does that limit need to exist, it actually needs to be equal to the function's value at that point. So two things have to work. The limit has to exist, and the function has to be defined there, and they have to be the same exact value. If it doesn't work out this way, then we say it's discontinuous at that point. So let's talk about what's happening at the discontinuities. So who's going to volunteer? Where's my first discontinuity? Go ahead. At -3. -3. So let's look at x equals -3. If you watch the videos, you probably picked up that you're going to have discontinuities anytime your graph has a break in it or anytime it has a hole in it. So you could say, yeah, it's discontinuous here because obviously it has a little a jump in the graph. And we call this a jump discontinuity. I put up here on the board the different types of discontinuities that we have. That's called a jump discontinuity because the graph jumps, right? Jumps from here to here. But let's look at it in terms of the definition, why it doesn't work. First of all, is f of 3 defined? Oh, sorry, -3. Is f of -3 defined here?
Yes.
What is it? 1. So the right side of this is 1. Agreed? I'm going to erase this so I can fit this in here. The question is, for there to be continuity at the point, I need this limit now to also be 1. But what is the limit as x approaches -3 of this function? We just said it didn't exist, didn't we? We said as you come in from the left, it's one thing. From the right, it's another thing. That means the limit doesn't exist. Understand? So does not exist definitely doesn't equal 1. since these aren't the same, it's discontinuous there. Understand? Okay. Where's the next discontinuity occurring? At -2. Now, again, we have a jump. But what makes the continuity definition fail isn't the fact that it's, what, undefined there? Like, is our function defined at -2? Yes. Yeah. It's the limit part of it that doesn't work, right? As you come in from both sides, it's not going to the same place. Where's the next discontinuity occurring? 0. Now, what is it that is causing the problem at 0, though? We call this a removable discontinuity. But is the limit the part that's causing the problem? No, because the limit is what? The limit, as x approaches 0, of the function, right? We know that this side, this is equal to 1. But for continuity, we need that to be equal to f of 0, wouldn't we? But what is f of 0? Undefined, right? I did not put anything here, right? There's no, the function is not defined at 0, so you can never have a limit exist. I mean, sorry, you can never have continuity at a place where the function isn't even defined. So how could I have done it? I could have done this. I could have filled this in like that, right? Would that have given us continuity? Because it's defined now. No, because it's not the same. I would actually need it to be what? 1. I'd need this to be 1. So I would come in here, and instead of doing that, I would fill it in right here. And that's why they call it a removable discontinuity, because removable discontinuities are easy to fix. You just have to change the function's value at that one point. If you can do that, then it's removable. Is this removable? No, because the limit's so screwed up, coming in from the left and right, there's no way to easily patch this thing up and make it work unless you somehow move this piece all the way down. You're going to change a lot of the function to make that happen, aren't you? Or if you move this piece up, or if you move them together, that's going to take a lot more than just redefining one point. See why we would call it removable versus a jump? All right. Next discontinuity would be at 1. And this is a jump discontinuity. No easy fix for that. Is it the limit part of it, or is it the function part of it that's screwing this up? The limit part. Next one. Jump. It's both the limit and the function aren't defined. I mean, it's a combination, right? How about at 2? Is the function continuous at 2? Yes. Yes. Because first of all, is it defined at 2? Sure. Is the limit from the left and the right, do those limits exist? They're going to the same place? And that's exactly the point that it's defined to be? It's continuous there. So what we like to say is that continuous functions are functions that you can draw without picking up your pencil. If you ever have to pick up your pencil, you've got a discontinuity. And then they talk about left and right continuous. So continuous to be continuous is a very, very strong condition to be continuous at a point. But then we have a weaker condition, a lesser condition, which is called left or right continuity. So look at this right here at -3. At -3, the part of it that screwed it up was the limit, right? But if we only look at the right side, so we ignore this, and we only come in from the right, then would it be continuous? Yes. Yes, because is the function approaching something? Yes. Is it approaching the function's value there? Yes. So this would be considered to be right continuous. Now, let me put this piece back in. It's right continuous here, but not left continuous. So at -3, it's right continuous, but not left continuous. Is there any place on this graph where we had a discontinuity, but it is left continuous? At 1. At 1, we had a discontinuity, didn't we? But it is left continuous here, isn't it? Is it right continuous at 1? No. How about at 2? Well, left and right continuity would mean continuity. And we already said it was continuous here. Here?
No.
You don't have either left or right continuous because what would you need for that? To fill one in. So someone tell me where to put my dot if I want this to be right continuous.
At 1.
At 1. Fill it in here, right? That would be right continuous. Look like my finger drew in black there. Okay, and then if I want to make it left continuous, I do this, right? Could I make it both left and right at the same time? Could I do that? Why not?
It can be defined in two spots.
That's right. This would fail the vertical line test, and then it wouldn't be a function, right? That would fail to be a function overall. So we got to remember that part of it is always at play. And everything we look at in this class, well, at least for some time, we're always looking at functions of x. They must pass the vertical line test. Okay. Does that kind of clear up some of the cobwebs that you may have had in continuity as far as visual part of it? Some of it? Okay. You want to ask me your question now? Did you still have a question?
Oh, basically I have a question on the very last problem.
All right. Is everyone comfortable in here with me moving the test till next Wednesday? Anyone have a strong objection to that? Anyone have a strong objection? Okay. We're going to move it to next Wednesday. Now your question. You're saying the last problem? Which page are you on here? Is this out of continuity? Okay. Do you know what number it was? Okay, 30. Oh, great. Perfect. This is the next thing I wanted to talk about. Okay, good. So from college algebra, we have this idea of what are called piecewise functions. And I know that this is covered in college algebra because I just covered this in college algebra today. So the idea of a piecewise function is that you have a function and you define it to be different functions. And so on a certain part of its domain, it looks like something, and then it switches to something else, and then it switches to something else. And so a very basic example would be something like this. x squared minus 1. And let's say x less than 0, x between 0 and 1, and x greater than 1. I'm just doing this to give you a picture of this. You don't necessarily need to copy this all down unless you really feel like you have to. All right, so if I were to graph this, what this means is that it's this function, which is the diagonal, the identity function, as long as I'm left of 0. So that means here's the diagonal. Left of 0 means this way. I don't put a solid dot because there's no equality there. When I get to 0, and between 0 and 1, I'm x squared, which looks like parabola that opens up like this. And here's 1, right? That's when I stop it. And it's actually defined there and there. Do you see that? And then here, after 1, I'm x squared again, but move down 1. So it's this picture, move down 1, but starting here. So shouldn't it go something like this? It actually goes like this. But I'm only drawing it from to the right of 1. Yes? And so this is my picture. Is this function continuous everywhere? No? You have a discontinuity? Where?
At 1.
At 1. Is that the only place? 0? That blue was filled in, right? So am I continuous at 0? Yes, I'm coming in from the left and the right, same place. It's defined there. I'm continuous. Here, though, I have a jump discontinuity. Yep? Understand? Okay. That's not what the problem you're asking about is, but it's connected to this. What they do is they give you, and this is a test problem for sure. This is something like what I'm about to do. They give you, it was 34 or 33? 34. 34. they give you a piecewise function. I think I'm going to need a little more space for this. Make sure I'm coming out on camera here. F of x equals, okay, x squared minus 4 over 2, over x minus 2, ax squared plus bx plus c, oh, no, plus bx plus 3, minus bx, shit, sorry. And then 2x minus a plus b. If x is less than 2, here, if 2 is less than or equal to x is less than 3, and here, if x is greater than or equal to 3. What is the difference between this piecewise function and the one I just put up on the board a second ago? Yeah, you couldn't graph this if you wanted to, because you don't know what a and b are, do you? Right? But what you do know is that this is a rational function from college algebra. This is a quadratic function or a parabola, and this is a linear function. If we're assuming a and b are just numbers, this would be a line, a parabola, and a rational function. That's what we have. And so if we graphed them, we should have, what, in this region, there's 3 different regions, we should have like a rational function, then a parabola, and then a line, yeah? So what is the question asking?
He's saying where A and B, like, I didn't write the question.
Okay, I'm sorry, I thought you had the book. So
The values of A and B that make F continuous everywhere.
find the values of a and b that make the function continuous everywhere. Which means that if I just tweak the numbers a and b here, that's going to change the shape of this, isn't it? If I use a negative a, it's going to open down. If I use a positive a, it's going to open up, right? If I change the b value, that's going to have an effect on the picture also. But whatever I choose here, I have to choose the same thing here. Whatever I do here, I have to do here. That's going to change the shape of the line. Figure out what a and b need to be so that when you draw this, you can draw it without picking up your pencil. That's what we're trying to do. Understand? 3 pieces of a picture need to be put together in a way that you can draw it without picking up your pencil. Okay. We good? I'm going to do all of this without drawing a single thing. I'm going to use strictly the definition of continuity. All right? Do we all agree that this function right here is continuous everywhere if I don't restrict its domain anywhere? Like, is that continuous on its implied domain? Why?
Because it's got the x minus 2 at the bottom, so it have an asymptote.
It has an asymptote, so where is it here?
But its implied domain means that it's not 0.
So in this notes here, we have this theorem. Okay? The theorem said functions which are continuous. All rational functions are continuous on their implied domains. This function is actually undefined at 2. Right? It's undefined at 2. But everywhere else, it's continuous, because that's what the theorem says. All rational functions are continuous on their implied domains. So everywhere except 2, I should be able to draw it without picking up my pencil. So my question to you was, is that continuous on its implied domain? Yes. Is this one continuous on its implied domain? Yes. Why? Because it's a polynomial function, right? So that's continuous on its implied domain. And this is a line. All lines are polynomials. So I know that the 3 pieces by themselves are all able to be drawn without picking up my pencil. It's just really where they're switching that I'm concerned about, right? Where I switch from one picture to the next. So the way I'm going to do this is as follows. I need continuity at x equals 2. Do you agree? 2 is the first place where I'm switching from one function to the next. That's the first place of interest. I need the continuity at that point. So let's write down what we mean, what we would need. Like what does being continuous at 2 mean? So we need let's see here. Who wants to tell me for a little bonus point here? This isn't, I'm not giving you like a hard problem. I just want to volunteer to tell me what the definition of continuity would mean there. Go ahead.
What the it's a limit of the
Okay.
of x.
Give me exactly x going towards 2.
At x squared minus 4 divided by x minus 2. That function, the first function?
I'm just going to put f of x. Is that okay?
Okay, yeah, that's fine. And it equals f of 2.
Okay. Good. Make sure I got you. Ryan, okay. That's the definition of continuity. Right? That's the definition of continuity at 2. I need this to be true. All right, well, how about f of 2? Do we know what f of 2 is?
Yeah.
Which of the 3 pieces of the function do you use if x is equal to 2? The second piece, right? Because that has the little equality. X, if x is 2, 2 is bigger than or equal to 2. So replace all your x's with 2's, and what would it become? 4a minus 2b plus 3. 4a minus 2b plus 3. That's what the right-hand side would become? You following me? Now, the way you work these, okay, so when you get this on a test, the way you work it is you're working left and right-hand sides down. Okay, I'm not writing like this is equal to this is equal to this. I'm working both sides, and I'm trying to make them equal each other. Okay, no questions on this? Okay, now this limit. What is the limit as x approaches 2 of the function? So I'm approaching 2.
So be x first minus 4 over.
Do I use the first one, the second one, or the third one?
First one.
Okay, first most. Let's rule out the third one. Why would I rule out the third one? That's near 3, right? Limits were real close to where you're going. I don't want to even be messing around with 3 because I'm getting close to 2, right? So throw out the last one. Why not use this one?
Well, not only that, but that has to be 2 or better or more.
What does?
The x value that we're approaching.
We're approaching 2, right? But that means from both sides. Right? Limit has to work from both sides. Yes? So if I was a little bit bigger than 2, I would be here, wouldn't I? What would happen if I plug 2 into this?
Same thing.
I would get the same thing. So what you would be saying is that 4a minus 2b plus 3 equals 4a minus 2b plus 3. Congratulations. You have no information there, right? So even though you could plug it into this, you already did. And so what you're doing is you're looking at approaching 2 from the other side, which would be this one. Understand? And so if I plug 2 into this function, or I'm sorry, if I try and let x get close to 2 in this function, then this limit becomes limit x approaches 2 of x squared minus 4 over x minus 2. I need these to be equal. Does everyone understand why I picked the first one? Yes? That limit, let x approach 2, what do you get? 0 to 0. But, what? Algebra. The left-hand side, right, this difference of squares cancels out a factor. So I'm going to continue over here. I have limit x approaches 2 of x plus 2 equals 4a minus 2b plus 3. So difference of squares, the x minus 2's cancel on the left with x plus 2. Can you take that limit now? What do you get? 4. So you have 4 must equal 4a minus 2b plus 3. right? Does anyone have a question on what I've done so far?
How do you get the x plus 2?
Difference of squares,
Oh, okay.
cancel one of the cancel the x minus 2 factors.
So we can always know that if x is approaching 2, we'll always know that x, if it's less than 2, we'll know that that's correct because it's less than 2, so we're approaching 2.
We're approaching 2. Well, but see, if I go a little bit bigger than 2, I'm still approaching 2. The reason why I didn't use this one is because that's where it was defined at 2. So if you want just kind of a rule of thumb, whichever one you use to plug in to get the right side, use the other one for the limit side. But I want you to see you could have done the limit for either one, but one of them makes sense, the other one doesn't help you. All right, what we have here is what would be referred to as a linear equation in 2 variables. You can never solve a linear equation in 2 variables, can you? I mean, you can solve one variable in terms of the other, but you can't get me a solution this way. And the problem said to find A and B, right? But what?
Can you substitution?
The third equation.
Well, this is one equation, right? I have one equation.
And use the third one to do a.
Okay, you meant third equation. So remember what I started at. I said, look, I know these functions were continuous, but I'm looking at where I paste them together. I said, okay, well, let me look at the first place that I pasted them together, which was at 2. And when I did that, I came up with a single equation, but 2 variables in it. What I haven't done yet is what?
3.
Looked at where it pastes together at 3. And if I set up a new problem, a new continuity problem, using that other place where they're pasted, I should probably come up with another equation in 2 variables, shouldn't I? And then I will have 2 equations in 2 variables, which you can solve using elimination or substitution. Got it? So let me set it up. So I've got that so far. Question, I'm kind of like, all right, where do I go now? So I need continuity where now? At 3. Which means I need the limit as x approaches 3 of the function to be equal to f of 3. That's the definition of continuity. I remember as a calculus student, like continuity was the first place where I started to realize, I don't know, that things were not algebra anymore. Like it just wasn't algebra anymore. It was more than algebra. We're using a definition to come out with a result, which is a lot different than just the mechanical stuff from algebra, right? I mean, this is a definition. I'm using it for something. I don't know if that makes sense. Okay, let's just keep going. What's the right side?
Wait, 2x minus, or 2.
You're going to use this one?
Yeah.
Because we got equality there? So replace the x with 3. And what would you get? 6 minus a plus b, right? I need that to be equal to the left side.
So would you use the for new formula you got, or the old?
Well, I'm going to use a limit. No, don't mess with this. I'm done. I'm paused here, okay? I'm just paused on that. I'm coming back to that in a minute. I need to approach 3. But which part of the function do I plug in here? The middle one, right? The second one? Because I don't want to use this one because I just used this one to get the right side, didn't I? I plugged 3 into this. I use this one because if x is really close to 3, then it's less than 3. So I use the middle piece. Why do I use the top piece? That's way near 2. I'm not worried about that. So I'm going to plug 3 into this for x. What would you get if you plug 3 in there? Well, let me write it down first, and then we'll actually do the limit. X squared minus bx plus 3. So replace x with 3. This is just a direct substitution. 9a minus 3b plus 3 equals 6 minus a plus b. Now there's my second equation. I have 2 equations with 2 variables. Yes?
Real quick, rhetorical. If the equals had been under the other 3, or before the other 3, yeah, had it been the other one,
that equation would have been on the right.
This would have been on the right. This would have been on the right. And then you would have the limit of this one on the other one, on the left side. Yes. Yep. That means you understand it. Yes. Okay. 2 equations, 2 unknowns. Let's solve this. So I'm going to take the first equation, and I'll take the, well, why don't you see if you can solve it? This is a college algebra thing. See if you can real quick. See if you can take this equation, and I'll clean it up for you. 4a minus 2 minus, I got that way, minus 2b equals 1. That's one equation. The other one, let's see, 10a minus 4b equals 3. Someone confirm that you got the same equations, yes?
Yes.
Okay. In college algebra, we like to use a brace on the left-hand side whenever we had a system of equations. Do y'all remember seeing that in college algebra class? And now you solve that system. There were 2 ways, substitution or elimination. Substitution is where you take one of these equations, solve it for a or b, plug it into the other equation. Elimination is where you scale these and try and get things to cancel. Yeah.
Could you use a matrix?
You could do matrices. Yep. However you want to do it. But this would be something you need to be able to do. I'm going to work through it. But while you're doing that on your own, I'm going to actually get this thing ready to graph something for me. As soon as someone gets an answer, please raise your hand if you have it yet.
Well, what I did was I multiplied this one by I was able to cancel those 2 out and solve the, so now it's
Think you got it? Okay. Hang tight. Let's see.
this one, the first one. And then I tried to solve 3. First 2.
Okay, we got a couple.
You said for both variables, right?
Yes, A and B.
I guess you could do either top or bottom, just so that the 2b would cancel. Because up there, you moved it first, you moved over the, because at first it was like this, right? We moved over the 4 onto this side, and so it made it -1. Now it's 6 here, so it made it be -3. So plus 1. And that just made it -1, so it's -2a plus 2b plus 3.
How many of you think you have the answer? Okay. All right, so let's see. What do you got for A and B?
A equals 0 and B equals -1.
A is 0, B is -1/2. Anyone else get that? I don't know. No? No? I don't know if that's going to, because if a is 0, we're not going to have quadratic anymore. Okay? What method did you use? Did you use elimination or
I did.
like substitution?
I eliminated first, and then I
Okay.
substituted.
Okay. All right, what's another, that's one candidate. What else? Who else has something else? Both or 1/2? Both?
A 1/2 and B -1/2.
B is -1/2? Okay, let's see. All right, so if I were doing this problem, what I would do is elimination. And so I would look at the A's and the B's, and I would try and figure out which one I want to kill off. And I think I would want to kill the B's off here. So what I would do is I'd multiply the top row by -2. If I do that, this new system of equations would become -8a plus 4b equals -2. And then this would be 10a minus 4b equals 3. And so what I've done is I put positive 4b here and a negative 4b here. And now if I add straight down, I get what? 2a equals 1, which means a is 1/2.
Oh yeah, I just did that. It's 1/2.
1/2, 1/2. And then to get b, how do I get b? I can just take a and plug it into any of these equations. So I'll just grab this one right here. And let me replace a with a 1/2. So what's 1/2 of 10? 5 minus 4b equals 3. Move the 5 over, or I'll move the 4b over. I'll move the 3 over. And you get 1/2 for b. Assuming we did everything else right.
Yeah.
Okay? I did that pretty quick. I hope those were the original equations. All right, there's a way to check. There's a way to check this. Do you mind hitting the lights just over here real quick? So what I'm going to do is I'm going to go out on a limb here because I don't know if this is going to work. I'm going to use this program called WinPlot. I think I've used this in here already. What I'm going to do is I'm going to have it graph the equation for me. The first thing we had was x squared minus 4 divided by x minus 2, right? And that was only on a certain interval. It was only until x got to what? 2? Okay, here's that graph. It actually turns out to be a line because it was a rational function, wasn't it? But when you cancel, remember you factored out and canceled, you were left with x plus 2, which is a line. But it has a hole. It actually has a hole at 2. All right, so that's the first one. Let me see. I'm going to put the other one in here. The next one we got was ax squared minus bx plus 3, wasn't it? Yep. A for us should be 0.5. 0.5 times x squared, I don't know if y'all can see me typing that in there, minus b minus 0.5x plus 3, but this was only on the interval from 2 to what?
It was plus B.
Was it plus? Was it plus b? It was minus b. So minus. So tell me what should happen when I do this. It's going to draw what? A parabola that opens up in some sense. But where should it be connected to? It better be connected where that red one stops. And like I said, I didn't work this problem out before class, so. Okay. Okay? There, that's the little parabola part. And now the next one, which is what, 2x minus b, no, minus a plus b. So minus 0.5 plus 0.5 is 0. So just 2x. And that piece, when I graph it, should connect that blue one and just go out to the right forever. Ah, I forgot to restrict its domain. I want to lock it. That was only from what, 3 on? There you go. That is a piecewise function. We found the a and the b that connect together those 3 pieces and make it continuous. Now, the real purpose of a problem like this isn't because you would ever really need to do that, but this really shows how you use the definition of continuity to actually come up with these values. You have to understand continuity pretty well to do this. And then there's systems of equations. It's a good problem. Okay, anything else from continuity? I would expect that if I give you a graph, you'd be able to tell me where it's discontinuous, left and right continuity, those types of things, and then a problem like this. Nothing else? All right.
How's that work with trig functions?
What's that? If you were to take several trig functions and do it, that'd probably be a little harder. Your systems of equations would probably wind up being things that would require some assistance to solve. You probably need, remember in college algebra you did like that RREF function on your calculator to solve a system of equations? You probably need something like that because the numbers wouldn't be nice like this one was. But you still do it the same way. All right. We are going to move on to 2.2. Because we already did 2.1. Can we get the light back on, please? All right, the main result from last class was that we had come up with the definition of the derivative, hadn't we? That was the main result. And it was that f prime of a was the limit as what? X approaches a, f of x minus f of a over x minus a, right? That was the definition. And remember we got this from a picture, didn't we? The picture that we had was we had a function, we had some value a, we had some value x, and what we wanted to do is find the slope of the line between those two, right? And then we said move that point over so it lays right on top of the other one. We already knew that we were going to get division by 0, but we knew that there was a way around it. So what we did is we said let x approach a, right? And we did rise over run and got that. Yes? Okay. Now, if we do a different picture, and instead of me calling these 2 points, A and then X, I could call it what? C and D, or I could call it Q and R. I call it whatever I want to call it, right? So what we're going to have here is a second definition for the derivative, an alternative notation. And here's how it works. If you let this be X, and this be x plus some number, h, where h here is a positive number. So like if this is 3, this might be 3 plus 1. Or if this is 3, this might be 3 plus 0.5. But no matter what, whatever this x value is, this is just a little bit bigger than it. Understand? Then I can still come up with the slope of the line between those by doing rise over run. So remembering that this point would have the coordinates x plus h, f of x plus h, and this would have the coordinates x, f of x, right? That's what this would mean. Plug in x into the function, you get the y value. Take x plus h, plug it into the function, you have the y value. Then what would rise over run look like here? Because it wouldn't be this, it would be a little different. it would be f of x plus h minus f of x all over x plus h minus x,
So just say,
just h. And then how would I move this point over on top of that one? I would make this one move over, right? How do I make x plus h get closer to x?
X approaching two?
Not subtract, but you're on the right track. Make h get what? Smaller and smaller, right? Instead of doing this and just saying, hey, look, I'm going to let x get close to a, here I'm going to let h go to nothing. If h goes to nothing, it moves that over, doesn't it? So what I'm going to do instead is I'm going to put limit, I'm going to let h go to 0 here. If I do that, the answer here should be the same as the answer here, shouldn't it? Exact same answers. So this is also the derivative, but here we would say it's not the derivative at a, it's the derivative where? At x. These are two different definitions for the same exact thing. Exactly the same thing. So what I'd like to do is a very quick example. So you can see the two definitions being used. So as an example, find derivative of f of x equals x squared at x equals a, then at x. So in other words, what I want you to do is, for this one, use first definition, and then for this one, use the second definition. So you have to remember, in the first definition, we called the point we were looking at a, didn't we? So that means I wanted the derivative at a. Here, I'm calling the point that we're find derivative at what? X instead of a. So that's why I'm asking at a first, then at x. So I'm going to use the two definitions. So what I'm going to do is I'm going to work out two different limits and show that they give you the same exact answers. All right? But what you're going to notice is that the algebra in the two different problems is different. Hopefully you'll notice it. So let's do the first definition. So I'm using this. The derivative at a is limit x approaches a, f of x minus f of a over x minus a, right? That's what I'm going to do. And how would you do this? What would you replace here? Because I actually gave you the function. Go ahead.
F of x would be just x squared.
Okay.
F of a would be a squared?
A squared.
Or an
So just replace. What is f of x? I told you f of x is x squared. What is f of a? Well, that's just plugging a into this, a squared. So you get x squared minus a squared over x minus a. How are you going to handle that?
difference of squares?
Difference of squares?
That's one.
Cancel, cancel, and you're left with x plus a, right? Now let x go to a. What do you get?
A squared, or 2a.
2a. 2a? I know I worked through that fast, but are there any questions on what I did there? All right, let's use the other definition, right? The other definition. The other definition says that to do this, I need to find the derivative at x. I need to do the limit, this time as h goes to 0, of f of x plus h minus f of x all over h. So what is the top left of that one? because it's not the same as this.
It's going to be x plus h squared.
Limit h goes to 0. It's going to be x plus h squared minus, what's f of x? X squared all over h. I'm going to give you all a second to catch up with me here. I have your quizzes from, I guess it was last time. I'm going to pass these around. Please grab yours out of here. It was, I guess, a group quiz or something? I don't know. What happened? Did I tell y'all anything on that group quiz? Because I graded them. Some of them were like done right and some of them were off. It was a completion grade? Okay, I got to go adjust all the scores because I graded them all. So like some of you didn't pass them. So I'll fix it, okay? Just don't throw this away. Because I had a feeling when I was grading it, I was like, why would, if it was a group quiz, why would half of these not be right? Okay, so just take yours out of here. But one thing I do want you to notice is that if I pass this back, if you didn't get a passing score, then you have to obviously work on some stuff. But if you got a passing score and you have yellow highlighter through it, that means you got to work on your notation. Like carrying your limit the whole time, proper notation. That, yes, you got to the right answer, but it's very, very messy. It would be like, you know, writing a paper without having any periods or any paragraph separations, just all, you know, it's just bad math penmanship. So work on it. And I know that you all don't think that maybe that's important. And I don't think I thought the same thing when I was in Calculus 1. But, you know, if you move on and do engineering stuff and you have to share your work with colleagues, you know, you want them to be able to read your ideas. I mean, it's one thing to know and understand it and be like, I don't need to write it neatly. I know what's going on. But being able to actually communicate your ideas to somebody else on paper, I mean, that's a talent. It's a skill. It has to be developed. So if you've always had bad penmanship when it comes to math, you can work on it still. You know, I look back on my calculus work, it was terrible. Terrible. And I got better as time went on. So just work on those sorts of things. All right?
Legibility under time constraints doesn't really...
Yeah, no, I'm not saying so much for a quiz like this, but just like your homework, the things that you turn in. I know that you can still understand everything you're doing and have bad penmanship. But it's something that you can work on. That's all I want you to see, to try to work on it. But if you're doing something and you're missing limits, that's a big deal. Like the limit has to follow you the whole way until you actually take the limit. Okay, so I stalled enough here. Did you all figure out what was the algebra? What was the difference in the algebra here? You have to expand that out first. Limit h goes to 0. X squared plus 2xh plus h squared minus x squared over h. So expand this out, you get those three terms, then minus x squared. What happens here? The x squareds cancel, and then what? They all have an h in them, don't they? Every term has an h. And so we can factor an h out of the numerator, and that will cancel with the h in the denominator, won't it? So this will be limit h goes to 0. I'm going to pull the h out. I'm taking my time here. 2x plus h all over h. Cancel the h's. All that's left is limit h goes to 0 of 2x plus h, right? And let h go to 0 now. What do you get? 2x. What was our answer over here? 2a. Our answer over here, 2x. One of them was the derivative at a. You got 2a. The other one was derivative at x. You got 2x. They match, right? Same thing? Which of these two had easier algebra, do you think? The first one, this algebra was a little easier. Difference of squares, cancel, done. Yeah. This one, a little more had to happen, right? So it's not always going to work that way, though. Sometimes the second definition's easier algebra than the first definition. Sometimes the first one's easier than this one. So from here on out, if you're trying to take a derivative using the limit, you know you could use both definitions. It's really kind of up to you to figure out which one to use. A lot of times students will stick with one and say, that's the only one I want to use, but you need to have them both available to you. Yes?
Are you ever going to say specifically to use one or the other?
No. The only thing I'll ever tell you on a test is that you must use the limit definition, either one, as opposed to using the shortcuts, which are coming soon. Yeah. All right, we doing all right?
Is there a reason why there's two definitions there?
Yes. Because the algebra. Because the algebra on one is easier than the other. And, or no, different, sorry. Because the algebra is different. And sometimes we need that because you cannot do it with one of the definitions is not good enough. Like the algebra behind is just way too messy. So you go to the other one like, oh. Like I'm going to prove a shortcut today, and I'll show you that with one rule we couldn't do it, the other one, or one formula we couldn't do it, the other one we can. Yes?
Is there a way to tell by looking at the problem which one?
Not really. Mm-mm. Not really. That would be helpful. Okay, so looking at this, we started with a function. The example we just did, I started with x squared, right? That was my function. And I took the derivative of it using the second definition, and I got 2x, right? That was my answer. Agreed? X squared is a parabola, right? Parabola, it's a function. The derivative, 2x, is a line, isn't it? But it's another function. Would you agree? So, normally, when we think of functions, we think of something like a domain. Bless you. Like it would take a number and it would spit a number out. Like that's what functions do, right? Functions take in numbers, spit out numbers. This would be like maybe like x squared. Yes? That's what we're used to seeing. What I want you to realize here, and I'll draw the picture next to it, is that let's say our domain are actually a bunch of functions. Functions. And what we're going to do is we're going to send them through something and get functions to come out. So instead of numbers being transformed into numbers, I have functions being transformed into new functions. Then I should probably not call this thing here a function. What we call this is a functional operator. I'm going a little bit beyond the book right now because I want you to think of this. A functional operator. You could almost look as a function, traditional function, as like a number operator, right? Takes numbers in, spits out numbers. A functional operator takes functions in, spits out functions. The derivative is an example of a functional operator. It takes a function in and it spits a function out, doesn't it? The process of differentiation, taking the derivative, transforming x squared into 2x, this is called differentiation. Okay, this process. So theoretically, if somebody gives you a function, you have a way of finding this derivative. You have a way of transforming it into something, don't you? All right, so the notes are saying that in this section. Thank you. If we have